And here is a discussion and a key points takeaways for this paper. As we can see, the figure 1 to 3 is mainly about the purification of our target, the gamma AMS UTP molecule, and our RNAP, and the sigma dependence assay. Figure 1 is about the purification of the gamma AMS UTP. As you can see, here is a chromatography of that. And then the scientists try to purify our RNAP. The key point here, one thing to notice is that they don't use HISTAC for the E. coli because we already got enough E. coli, but they use HISTAC for the core enzyme from the M. bovis BCG and the M6 magmaticis to ensure that there is enough yielding of our RNAP from the mycobacteria. And then what they did is that because they only purify the core enzyme, and then they combine, reconstitute it with the sigma, because it tries to make that it only dependent for the sigma. Here is the core enzyme, and here are the sigma factors for the R3 mycobacteria. Also there's one thing to notice that for easy scale up, they only use 2 chromatography instead of the 4 whole procedure, which you can see there's the minor contaminant bands here. But to ensure the sigma dependence, they did a radioactive assay like in figure 3. So what they did, we can say here, in the 0% zero concentration of sigma factor, there's no CPM incorporation. With increasing sigma rate, they're increasing, which we have the science determine is dependent on sigma. Then in figure 4 and 5, they did a fluorescence assay using the mechanism in the introduction part. Before the HTS campaign, they use the gamma NTP to see the initiation, the elongation, and they draw the time course and the enzyme concentration of the curve. What they try to ensure here is that before going into the large, big, tremendous HTS campaign, they tried to do the fluorescence assay first to make sure that it was eligible for detecting inhibitors, this time the rifapine, in both the transcription initiation and elongation. Then it's figure 5 and figure 6, the HTS campaign. But first of all, let's look at figure 5. We can see there's 2 tests, and they also show similar trends here about inhibition rate. But we know they're rifapine resistance, but why isn't there 100%? There's no 100% inhibition for the rifapine. Why is that? And the maximum is 70% to 80%. So why are the maximum inhibition rate not existing this number? Here's a poll question. You can type in your answer by entering this website. So I will wait 30 seconds. Why is that? The rifapine resistance mechanism, I covered in introduction that it binds to the beta subunit of our RNAP, but the thing is that it kind of binds close to the beta strand, but it does not inhibit the first phosphodiester bond. So even though it directly blocks the elongation of the RNA, it already synthesizes 2 nucleotides or 3 nucleotides before the transcription stop. So you can see also in figure 6b, we can see there's with increasing rifapine and the fluorescence activity decrease, but there's still fluorescence activity. So what we use for the substrate is a thing called a T4-phage DNA. The promoter contains a large percent, it's 64% of AT. And here, the thing is that when transcription starts at A and followed by followed by pyrimidine residue. The incorporation from the UMP, because there's an A here, from the gamma AMS UTP, is actually already increased the fluorescence. And this step is not blocked by the rifampin. It's like the rifampin cannot block this. So even if this E. coli, this RNA, is blocked afterwards, it still increases fluorescence in the first steps, in the first few steps of the nucleotide incorporation. So that's why the maximum inhibition rate does not exceed 70% or 80%. And as we see before, there is a confirmatory assay for the HTS campaign, because like the gamma and the SUTP is not a good substrate for our mycobacteria. So they do a confirmatory assay. They use unmodified UTP to eliminate the false positive I just mentioned, and also they eliminated the weak inhibitors, which competes with the gamma in SUTP in the fluorescence assay. The results, the data is not shown, but they give the numbers. The results are promising. 80% of the HTS activity was confirmed, which means the percentage of the false positive and the weak competitors are incredibly low. And there's like 20% that are inactive. But nevertheless, it is still promising hit to lead. That's a promising result. For this, and for the conclusion of our HTS campaign, we use E. coli RNA-AP as a primary screen and M-Seps magneticus plus M. bovis BCG RNA-AP as a confirmatory assay. We use a fluorescence assay because that's one part, one step. There's no like radioactive, which involves like multiple steps. And the E. coli has been thoroughly studied. There's like homologous and the high yielding. So that's why we use E. coli first, and then we use non-human pathogens next. And for the HTS, we use a combination of a UHTS system and the offline multi-draw because of the technology issues. We try to maintain the background noises here. So in our HTS campaign, we screened 67,000 compounds in total. And with 80% active, we are in the process of hit-to-lead optimization of our RNAP inhibitors. The previous HTS had multiple drawbacks, including like here, multiple steps, and more expensive. They're expensive, but our fluorescence assay, none of the reagents are expensive, and one part, one step, and hit to lead is promising. So the researchers, like in this paper, they use the rifampin for the RNAP inhibitors, and they got quite promising result. So in the future researches, we can use other inhibitors. We can use our artificial inhibitor to screening for the mycobacteria RNAP, or even with like other infectious diseases RNAP to get the inhibition rate from the HTS campaign fluorescence assay. And that's all for this paper. Thanks for listening.